Hey again, everyone. A little bit more as far as relativity, and I like to call this kind of the WTF lesson. At least that's how it was for me when I learned this in college. Actually, this is kind of the weird lesson where suddenly you start to see the world and go, things aren't quite as I thought they were, or maybe how they should be. And there's actually this book, if you're a big kind of reading person, it's called Nausea, and it's by this guy called Jean-Paul Sartre, and he's this French author, obviously. So Nausea, Sartre's. It's this awesome book, and it's very bizarre, and it's actually about this guy. And so the Sartre is this French dude who wrote the book. The main character is a writer who's trying to write a book. So there's a little bit of writerception going on, and the whole idea is about this fictitious writer who's the main character, and he has these moments that he calls nausea, where things kind of just seem weird. Like he's sitting in a restaurant, he's looking at the drapes and he's like, why are they so purple? And he's just like, have they always been that purple? And then he like goes up to his hotel room and he's like, why does the doorknob feel this way? Has the doorknob always felt this way? Or am I kind of just waking up to how the world really is? Or is something wrong with me? It's kind of like, am I crazy or is the world crazy? And it's kind of these moments of nausea that happen throughout the book. And so it's really awesome. I would highly recommend it. And this is kind of one of those moments, at least how it is for a lot of people that are really into physics, because you're kind of going, wait a second, am I just kind of waking up to the reality of how the world really is? And so in our last little video, we talked about reference frames, we talked about Einstein. And so in this one, I want to talk actually about relativity and Einstein a little more, but also about light and this thing called the constancy of the speed of light. And so way back in like the 1800s, electricity and magnetism was like the hot poppin' thing, and everyone's doing all these experiments. And there's this guy Faraday, and Faraday kind of came up with this equation, and he said that the equation was that C is equal to 1 over the square root of epsilon naught mu naught. Now, my AP Physics 2 folks, um, this is something that actually comes up in the AP Physics 2 class, and epsilon naught is called like the permittivity of free space. It's like how the vacuum of space allows electric fields to pass into it and kind of occupy that space, kind of like how gravity occupies the space around wherever you're sitting right now. And this mu naught is the permeability of free space, and it's just how the vacuum of space actually allows magnetic fields to pass through and kind of occupy it. And it turns out that they're both just two really small numbers. They're really small numbers. And so it turns out that if we kind of go in and plug in for the permittivity, and we'll just put a really big square root here because these are kind of bigger numbers, we end up having, what is it? Epsilon naught is 8.85 times 10 to the negative 12 coulomb squared. That's like units of charge over Newton meters squared. I know those are super weird units. Just trust me on this one. And then the permeability is actually 4 pi times 10 to the, what is it, negative 7. And then that's Tesla meters. Teslas are units of like magnetic field over amps. And so if I take that and I actually go to my calculator, I do 1 divided by, and then I kind of do this whole square root thing of 8.85 times 10 to the negative 12 times, and then 4 times pi, and then our negative 7 here. Oops, negative 7. And we got an error. Where's my error? Oh, there's my error. Oh, come on. Nope. Okay. And lo and behold, I get this whopping number that's like 2.9986 blah 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 times 10 to the 8, and the units end up being meters per second. So really, we said in the last lesson that the speed of light is 3.00 times 10 to the 8 meters per second. That's where it came from. It actually came from electricity and magnetism. And that seems a little weird because you're like, wait, this is light. This isn't like a positive charge or like the magnet on my refrigerator. So what the heck is up with that? And so, and even more so, you're going, maybe you're thinking, well, didn't we just talk about relativity? Like, didn't the speed of sound seem faster or slower depending on the person, if they were in the plane or on the ground? So how do we get just one number for the speed of light? Like if I'm in my race car and I shine a light going forward, so if I'm going forward and the light's going forward, shouldn't those two speeds add together to give me a faster speed of light? Or maybe if my car's going forward and I shine the light backwards, isn't the speed of light going to be going slower then actually, right? Kind of weird, right? So it turns out, and you had me for Honors Science Academy too, that light is an electromagnetic wave, and we even learned a pretty snazzy dance about it. And so it turns out that if I kind of drew my electric field like this, and we'll see. I haven't done this drawing in a while. I didn't practice, so you'll get to see kind of a good old cold turkey drawing for it. Um, let's say that this is our electric field. So we have kind of E in the electric field as a vector. It has a direction, so we put the little hat on it. And then we have kind of our magnetic field, and then it kind of goes like that, and then comes around town right there, and then it comes right on through there. And now we kind of got to make it a little 3D, so we're going to erase some of the parts here. And so the parts that are erased are parts that you actually would not see if you were looking at this. And so the whole idea is that this green one is going up and down and up and down, and the blue one is actually coming into the page and then coming out of the page towards your face, then going away from you and then coming back out, and then going away again and coming back out. And so this is the magnetic field. So the weird thing about it, kind of tying this all together, is that light is this electromagnetic wave. And the freakier thing is that it's self-sustaining, like it keeps itself going. And so, and this is more of an AP Physics 2 topic, but if you have like a field that's electric, an electric field that's kind of alternating, it's oscillating, it's going up and down and up and down, that creates a magnetic field that we see here in blue. But also, if you have a magnetic field that's kind of changing, like we see here, going this way and this way and this way and this way, that actually creates a magnetic field or an electric field. And so these two kind of work to sustain each other, and it's really bizarre, I gotta say. And so this guy Faraday came out with this equation, and everyone's going, well, wait a second. This gives us one value for the speed of light. There's like no freaking wiggle room. Like, what the heck is up with that, right? Why is it just one? And so young Einstein, back in his day, was wondering about this. And he's kind of thinking, he's going like, well, how would a light wave look to someone that's like surfing the wave or traveling with the wave? Like if the speed of our light wave is actually kind of going this way, shown in red, that's like the velocity of our wave. Like, what if you were right here? Let's make me tan. There, I'm dark now. And if I was going this way at the same speed as the light, that's the idea, right? So if I'm going that way at the speed of light as well, what would it look like? That's really what Einstein was kind of wondering. And so is it kind of like a water wave? Is it like a sound wave? What's kind of the idea with that? And so what really happened with Einstein is he came up with this idea, and it relates to these inertial reference frames like we were talking about. And just before, we were saying that, well, it's a frame where all of Newton's laws is what we said before. All of Newton's laws are valid. Well, Einstein kind of went one step further, and he kind of had this leap in a way. And he's saying that, really, what if all the laws of physics, literally all, not just like a couple? So what if this whole idea is that an inertial reference frame is one where all laws of physics are the same, And so this is something that he actually came up with. So we'll call this Einstein's principle of relativity, or maybe just principle of relativity for short. Principle of relativity. This is the idea that all laws of physics are the same. In inertial reference frames. So now here's where things get a little weird. So the weird thing with this though is and here's where it kind of gets into the WTF part of today's lesson, really, with Einstein, is if all laws are the same, that means then that all of Faraday's laws are the same, these ones. Well, if all of Faraday's laws are the same, that means that the answer from them is the same. So how can it be then that the speed of light is the same in all reference frames? Because that's what that means. If all laws of physics are the same, then that means this equation is the same in all reference frames. That means no matter how fast you're moving, the speed of light is the same number. It's not going to slow down compared to you. It's not going to speed up compared to you. And so that means that light travels at the same speed c in all reference frames. And so that's super whack. That doesn't make any sense at all. You would think that, hey, if you're over here, and if I am moving, so if I'm sitting still, that's what this one really is. So this is sitting still. That's reference frame S here. If I'm sitting still and I beam my flashlight, the light wave goes out at the speed of light. See, cool. If I'm sitting here and I'm moving, that's what reference frame S prime is. If I'm moving towards the light, you would think that, well, the light would appear to be a little slower. The speed of light minus my velocity, because I'm kind of trying to catch up to it. I'm not going to catch up to it. It's fast speed of light, but it's going to seem a little slower. That's wrong. That's what people thought. It seems as if the speed of light should be different, but it's not. Now, here's another way of looking at it. If maybe Kathy here is on her bike, right? Kathy's on the bike, and Amy and Bill are both going to shine a light at her, okay? You would think that as Kathy moves towards Bill's beam of light, it would kind of be like our plane example, right? It would maybe be kind of like this one, right? If I'm moving at 200 to the right and the sound wave is moving at 340 to the left, well, it's going to seem like the sound wave is moving at 540. But it turns out that in this case, if I'm moving to the left at 90% the speed of light, that's 0.9 c, so I've got some strong legs, or Kathy, I guess, in this case. You would think, well, the speed of light here, this is always moving at c, and then this one's also moving at c. You would think that this beam of light from Bill would look like it's moving at 1.9 c, because we just added them earlier with the plane example. But it turns out that that is not the case. That is not the case at all. It means really that the speed of light travels at c in all reference frames. And this is something that's kind of weird. And I'll talk about how we actually know that to be true in just a second. So the speed of light c is the same in all inertial reference frames. Now, this is actually called the constancy of the speed of light. This is actually pretty important. Maybe we just make this in Galaxy. So get your Galaxy pen out. This is called the constancy of the speed of light. And it's weird. If you feel a little uncomfortable, that's perfect. You probably should, in all honesty, because the speed of light is the same in all reference frames. That's very bizarre. It goes against all kind of common sense. It goes against all personal kind of intuition. You would think that it would be just the same as the sound wave and the plane on our previous page, but that's just not the case. Now, I just want to tell you there's a pretty cool story about how people kind of figured this out and proved it. It was really hard in the 30s, though. There are these two guys, I think it was Kennedy and Thorndike were their names. They used the entire Earth itself as a laboratory, which is just in and of itself pretty freaking awesome, right? So the whole idea is they have the Earth, and well, we have kind of the sun here in the middle, yeah, right. And so the sun's here, and they took the Earth, and the Earth, let's say, goes this way. I'm just arbitrarily making up a direction, all right? Um, and the Earth typically goes about 30,000 meters per second around the sun. That's how quick it's going. So we'll say that V here is 30,000 meters per second. We'll say it's negative because it's going to the left over here, and that's fine. So, and the laboratory is on Earth, of course, right? So the Earth is the lab. And so the whole idea they found out is that between January and July, then, well, if the Earth is down, let's say this is in January up top, and let's say this is July down here, well, now it's going 30,000 meters per second here. And now this is a positive value because it's going to the right. So we have a total difference in velocity of 60,000 meters per second, because it's hard to get stuff going really fast to compare to see if the speed of light is the same, right? Because if you're in your car, it's hard to take good enough measurements to figure out if you're getting close or not. But by using the Earth as the laboratory, they were able to kind of take some measurements and find out that the numerical value for the speed of light is actually the same to within, I think it was, when they took the values here, they got that, I think they got that C here was like 3 times 10 to the 8 meters per second, plus or minus, and I think it was plus 2 meters per second. And I think when they did it actually later, they got exactly the speed of light. Oops. So really kind of plus or minus 2 meters per second, they were within an incredibly small margin of error. They were very, very accurate. And so they did it this way and they got this value. Now, aside from that, I'll just kind of mention right now that we also can tell that this is how things are. Actually, I'll wait. I'll talk about kind of some weird particle physics later. So maybe you're going, okay, I get what you're saying. I hear the words that you're saying. I still I don't agree. Like, that cannot be true, right? And if you're kind of in that position, that's perfect, because I hope you're being very critical right now, because it seems like I'm just telling you fantastic lies to kind of just keep you interested, I guess. So it seems really weird, but I want to talk about how that can kind of be so and what that must mean. And this is kind of a weird, harder topic to explain, but let's maybe look at kind of this picture right here. So we got to do a little throwback though. We know that velocity, right, is change in displacement over change in time. And now really they used U in this textbook I store pictures from, but let's just make these V's. So V and V, let's make this V prime, and here's V prime again. Okay, so we'll just kind of do that for it. Well, another way to look at that then is really that we could kind of rearrange it, and we could say that, well, velocity times time would give us our distance then, right? If I just multiplied the t here over to that side, that's what I would get on this right side of this equation. So you can kind of look at it these two different ways. Now, how can that be true? How can we have it that in two different reference frames, we have the same speed of light? Well, honestly, here's kind of the weirder truth, and this is going to make you probably, this answer is going to give you more questions, I bet, than it's actually going to answer. But if we need to get the same value for the speed of light, so let's just kind of take this and say c, because velocity, we're going to use the speed of light here. Well, if it's the change in distance over the change in time, if I'm moving, Okay, so let's just think about this. If I'm moving, and let's say that this is reference frame S then right over here. So if this is me, or let's say it's you. Okay, so there you are. Cool. And then there you are later. Ha. Well, okay. This is the weird part to explain. You're gonna travel some distance, right? Some delta x, and it's going to take you some time. So we'll just say this is kind of our normal kind of version of it. Okay, so let's say that this is for S. Okay, now let's look at it for S prime. We said that the speed of light's the same. Okay, so if we have to get the same thing on the left side, the speed has to be the same. Okay, but if you're looking at reference frame S prime over here on the right, well, now in this frame, it looks like the person's moving slower to the right, but now the trees and the post are moving to the left. So this is kind of some weird, awkward reference frame where you're not the bicyclist and you're not the trees, but you're something kind of in between. So it looks like both are moving. Okay, you're not on the ground. You're something, maybe you're just walking here slowly to the right. If you're walking really slowly to the right, the bike's still going to be moving to the right, but now the poles and the tree are going to look like they're moving to the left. So it's going to look like the cyclist has moved a smaller distance. Okay, you can't disagree on that. So they've gone some value delta x prime, and this is smaller though, right? A smaller distance. Well, we have to get the same c value though, right? If they moved a smaller distance, we're gonna have a smaller thing on top. We have a smaller thing on top, we're gonna end up getting a smaller value for the speed of light, but that cannot be true. So at this point, we're just using raw logic here. You would have to agree that the only way that the speed of light could be the same in both of these is if, even though this person appears to have traveled a smaller distance, delta x prime, the smaller distance on the right here, it must have taken them a smaller amount of time, right? So really what I'm saying is if it appears they traveled, I don't know, let's just say this is 5 meters in 5 seconds. Well, we get 1, all right? Well, let's say this one then, it appears they took 2.5 and 2.5, because those two divided would also give you 1. So it would appear that for the speed of light to stay constant, and this is kind of where it gets weird, for the speed of light to stay constant, lengths might not always be the same, and the amount of time that passes might also not always be the same for things that are moving. And so we're used to saying, oh, well, a meter's a meter, a second's a second. A second isn't always a second to everyone. A meter in length may not always be a meter of length to everyone, and it depends on your reference frame. And that's where things start to get kind of weird. And so I think that maybe we just leave it at that for this video, and we'll kind of fill in a little more on the next one. So thanks.